Let's talk about these rational functions, graphing the rational functions. This has got a lot to it. So what I want to do right now is just go through all these basic definitions and such, and then I'll go through individual cases, individual type of problems, and have a separate video for each one of those. So let's start with the basics here. The degree of a polynomial is the highest exponent when it's written in expanded standard form. So when we talk about expanded or standard form, and I'm just making this up. This is not an example, and none of these examples are not going to correlate to each other. I'm just trying to make a point here. So if I've got something like 3x to the fifth plus 2x to the fourth minus 5x squared plus 6, see, that would be considered expanded or standard form. It's all multiplied out. The powers are in decreasing order. The degree is the largest power. So this guy right here would be degree 5. So the degree is the largest power. Now, when we talk about factored form, we had this on the last test. Factored form is when it's broken up into its pieces. So once again, these are not the same thing. I'm just making up just different examples. So if I had 2x to the third, I'm sorry, x minus 2 to the third, x plus 5 to the fourth, 2x minus 1 squared. See, this would be considered simplified factored form because everything is in their factors with their power on them, because the power is going to tell us how we're going to graph it. So simplified factored form, just like we did on the test, it's the factors. Okay, vertical asymptotes. Vertical asymptotes is when it doesn't exist. It's the zeros of the denominator. It's when a fraction doesn't exist is when you have 0 in the denominator. So if I had something like, like I said, I'm just making this up. If I had something like x minus 1 over x squared minus 4, well, that would be x minus 1 over x plus 2, x minus 2. Well, so this does not exist when x is negative 2 or 2. So, tell you what. So see, if I put negative 2 or positive 2 in here, the fraction's not going to exist. So that's going to create a vertical asymptote. It's where it doesn't exist. So we'd say the vertical asymptotes are x is equal to 2, x is equal to negative 2, because vertical lines always are x by itself. X equals x equals. Horizontal asymptotes, unfortunately, have a whole bunch of different rules. And I'm going to go through I'm going to make a separate video for each of these cases. So horizontal asymptotes have a whole bunch of different rules. If the degree of the numerator is great, like if you have 1 over x minus 1, the degree is 0, the degree is 1. There's an understood 1 right there. And there's an understood x to the 0. If the degree is 0, if the degree of the numerator is less than the degree of the denominator, you always have a horizontal asymptote of y equals 0, because horizontal lines are always y by itself. If you have something like this, the degree of the numerator equals the degree of the denominator. So this would be something like 2x squared plus 6, 3x squared minus 7. Then the horizontal asymptote would be y equals, the lead coefficients are 2/3. 2/3. Then our other case is if the degree of the numerator is greater than the degree of the denominator, it does not have a horizontal asymptote. Does not have a horizontal asymptote. We'll have that case eventually. Like I said, I'm going to go through all this individually in different videos. The degree of the numerator is greater than the denominator, it does not have a horizontal asymptote. So if you have like x to the third over x squared, it will not have a horizontal asymptote. It might have a slant asymptote, because a slant asymptote is when the degree of the numerator is exactly 1 more. So if you had something like x cubed minus 1 over x squared plus 7, this would have a slant asymptote because the degree of the numerator is exactly 1 more. Then the way you find that is we have to do the division. We have to divide the numerator by the denominator. This is where we may have to use long division, because you know how I kept saying we may have to use long division in the next unit. And that's what we're talking about here. Like I said, I will make a separate video and go into the slant asymptote in excruciating detail. All right, you've been doing this since you were little kids. X-intercepts are what make the entire thing go to zero. So if I have something like x minus 2 over x plus 4, and it doesn't even matter, x minus 3 over x minus 4. Okay, so if this is my function, if this is my factored function, the x-intercepts are when the entire fraction equals to 0. Well, the only way for a fraction to be 0 is the numerator. The numerator has to equal 0, because you know, like 0 over 5 equals 0. The numerator has to be 0. So what makes the numerator go to 0 is our x-intercepts. So we would say, oh, so x minus 2 equals 0 and x plus 4 equals 0. Now, x-intercepts are also points. So we would say, oh, so that means 2 comma 0, because the x-intercept is when y, f of x is y. So what makes the whole thing go to 0? What makes y equal to 0? And x is negative 4. So x-intercepts need to be written as points. X-intercepts need to be written as points, 2 comma 0, and the y-coordinate is always 0. What makes it equal to 0? Now, the y-intercept is simple. If you've been, you got x squared plus 7 and x to the third minus 3. The y-intercept is when you just put 0 in for x. So 0 squared plus 7, 0 to the third minus 3. So the y-intercept is just negative 7/3 in this cheapo example I'm doing here. But one more time, you put 0 in for the x, so it makes a point, 0 comma. So these have to be written as points. Now it's going to get weird, stuff you may not have done in Algebra 2. What we call the point of intersection, the POI, point of intersection. It's where you intersect either the horizontal or slant asymptote. And I know we're going to talk about asymptotes a lot. You're thinking, no way, you're never supposed to intersect an asymptote. See, that's not necessarily true. The asymptote is the imaginary line, or just the line you get infinitely close to. Either your x or y gets infinitely close to as your x or y goes to infinity. The problem with asymptotes is sometimes you can intersect a horizontal or a slant asymptote inside the graph. That's not when you're going out to infinity, but I always call it inside the graph. We'll do examples like this. So it is true you never intersect a vertical asymptote, but we will have intersections of horizontal and slant asymptotes. These are kind of a pain, to make up examples of, but that's we'll talk about this. I'll have this in a video where we're going to show very specifically with specific problems about the horizontal or the slant asymptote, and if you're intersecting it or not, and then how to graph it from that. Holes in the graph. I think y'all did this in Algebra 2. This is where you get some factoring and canceling. So if you had something like f of x equals x squared plus 2x plus 1 over x squared minus 1, and you'd say, wait a second, that factors into x plus 1 over x plus 1, x minus 1. Those completely mess up. So you'd say, oh, look, that cancels. So who's the 0 of the part that canceled? The 0 of the part that canceled is -1. So that means you're going to have a hole in the graph at -1 when x is -1, because that's the 0 of the part that canceled. But then you plug that -1 into what's left over. And this is not a good example, but we'll do more of this later. The part that's left over is this. There's your part that's left over, and now we're going to sub in the -1. So -1 plus 1 over -1 minus 1. So 0 over -2, which is 0. So your hole in the graph is at -1 comma 0. And we'll do an example of that later. All right, the domains, your set of x values. So what's going to end up happening is if we've got a graph that looks like this, So if you had a vertical asymptote where x is equal to 3, and then you had a hole in the graph at like 5 comma -1, see the domain, we would have to exclude because the domain is our left and right. Domain is our left and right. So we would have to exclude the 3 and the 5. So the domain would be, oh, that's -infinity to 3, but we have to exclude it because you can't, the vertical asymptote's not part of the graph. And now the hole in the graph, the 5 is not part of the graph either, so we have to exclude it. So the domain, we'll always be able to find the domain. Every problem we'll be able to find the domain. So those will work out. The range, we're not always going to find the range. Like on a problem like this, we could find the range. As long as there's no point of intersection, we could find the range. But we're not always going to ask you to find the range, because sometimes we're going to have graphs that look like this. We're going to have graphs that do something like this. And I can't find the range of this with what we know. I don't know what that minimum and maximum point are. So I could not find the range on that. But we'll talk about the range when we get to problems where you are capable of finding the range. So anyway, all this is going to be posted. And I'm going to make separate videos for all these cases to try to put it all together. Right? So this is going to be super fun. This is super fun unit, right? Okay.